This is your 8th grade science recap video for Friday, April 30th and Monday, May 3rd. We are continuing with star review today and are going to look all at day 3 of your review packet. We'll review mostly Earth science today, or Earth and space science. We'll talk about the Earth's rotation and revolution and how the moon's revolution causes our lunar phases. We'll review a little bit of astronomy and look at some HR or Hertzsprung-Russell diagrams. We'll review plate tectonics and then topographic maps and satellite views. For independent work, there will be a Kahoot linked here if you wanted to play an independent Kahoot to review some of those topics. There's also a good review at the bottom if you would like a helpful look and visualization at day-night and seasons, our rotation and revolution. As far as day 3 information, let's get the and look at the material we reviewed. So we talked about rotation, which is spinning, versus revolution, which is going in a circle around something else. And it is our rotation that causes day and night. So if I were to draw a diagram of the Earth, I'd make sure I had an axis, draw an equator. I'm going to make sure that I show that the axis is spinning, and that is called rotation. And then let's also draw a sun so we can show the cause of day and night. And so if I had my sun over here, for instance, the side of the Earth that's facing the sun is going to be getting the sun's light. So the left side, in my case, would be the day side of the Earth, and the night side would be the back of the Earth. And remember that this rotation takes 24 hours, so approximately half of that we are in daytime, and approximately 12 hours we are in nighttime. We also reviewed seasons. And with seasons and all of our Earth science topics, perspective is really important. One thing to remember is that our tilt is always tilted toward the North Pole. We are always tilted, our North Pole is tilted towards the North Star even. Sometimes though different diagrams are from a different perspective. Think of it as you're in a different place in space looking at this sun-Earth system. So we're going to look at 2 different diagrams. What we're going to do on each of these is we're going to label our seasons, our equinox and our solstice, and we're going to think about really the tilt of the Earth and why it causes those seasons. Notice in the top diagram, each Earth, as it goes around the sun, the North Pole in this case is tilted to the right. So if I wanted to even add the North Star or Polaris, it must be from this perspective on the right-hand side of my page. When we label seasons, always go to the sides first because those will be your extreme. So we'll start with summer. I always try to find summer first, and it's always going to be on the left or the right. And so we're asked to label things for the northern hemisphere. So for us above the equator, like Texas, we live above the equator. We live in the northern hemisphere. We're going to focus on the North Pole. And so we're going to find which side of the diagram, the summer, it will always be on the left or the right, that shows the North Pole tilted toward the sun. And in this case, position A has the North Pole tilted toward the sun. So that must mean this is summer. I know that the Earth revolves around the sun counterclockwise. There's even arrows to kind of cue me into that. And I have to remember the order of the seasons. After summer is fall. After fall is winter. Whenever I get to the sides, I do a quick check and make sure that it makes sense. In the winter, is the North Pole tilted away from the sun? Yes, it is. Continue. After winter is spring. We also want to remember our vocabulary words. Equinox sounds an awful lot like equal, as in day and night are roughly equal in length, and those occur both in the spring and in the fall. Solstice are our extreme seasons, and my memory trick, S for solstice, S for sides. Your seasons on the sides are your solstices. In the summer solstice, we are tilted, our North Pole is tilted all the way toward the sun, and it is the longest day of the year. In the winter solstice, the North Pole is tilted all the way away from the sun, and it is the least amount of daylight hours in the year. Now let's look at our bottom diagram and pay attention to the tilt. Remember up here we said that they were all tilted to the right, the North Star would be on the right. Don't memorize this is the seasons though, because sometimes we have a different perspective. Notice now my sun's still in the middle, but now my Earths are all tilted to the left. This is like I got in my magic school bus and I went somewhere else in space and I'm looking at the system again. So if I wanted to even add, here's my North Star. And now I'm going to go through and think of seasons, and again, go to the sides and find summer. So summer is going to be one of these two for the North Pole. I need to decide where does it show the top of the Earth, the North Pole tilted toward the sun. So the North Pole is tilted toward the sun over here, so that is our summer. And again, I have to go counterclockwise and remember the correct order of the seasons. After summer comes fall. After fall is winter. And again, when I get to the sides, I do a does it make sense check. Is the North Pole tilted away from the sun? It is, for sure. Keep going. After winter is spring. Again, I'm going to label my equinoxes. So my equal night and day, 12 hours day, 12 hours night, happen both in the fall and in the spring. And S for solstice. The winter solstice is when we have the least amount of daylight hours or the most nighttime hours. The summer solstice is when we have the most amount of daylight hours or the least nighttime. The season that we have the most daylight is definitely the summer. If we were trying to use a spinning basketball to model day and night, what would the student do in order to best model the cause of the day and night? Well, the Earth's rotation causes day and night, but the basketball is already spinning. So we need to think about, well, what are we spinning into or out of? And we're spinning in out of the sun's light. So we need a light source to give us half of the Earth being lit. So the best way to represent or model this would be to shine a bright light on one side of the ball. If I had a light source, then that would allow me to represent the half of the Earth that's in the day and the half of the Earth that's in the night. Which of these changes would likely occur if the rate of Earth's revolution increased? Increase means got faster. And revolution, that normally takes a year. That is the cause of our seasons. So I would eliminate C and D. Those have to do with our rotation. If we were going around the Earth, if we were going around the sun even faster, our year would be less. Our seasons would be shorter. If we look at the model below, we're asked to compare the conditions of location X and Y. And so there's kind of a lot going on in this diagram. I have the sun over here and X and Y here. One thing I notice is that both of those are in the daytime. Both of them are on the side of the Earth that's facing the sun. So I would eliminate A. Nighttime things would be over here, which they are not. D is telling me about the moon's brightness. This doesn't include the moon. They're both in daytime. That's not a relevant answer choice at all. Now I notice that my last two answer choices are about seasons or amount of daylight, which are kind of related. So let's figure out the seasons, because I notice that both of these are in opposite hemispheres. Y in the northern hemisphere is tilted away from the sun, and so it would be winter in the northern hemisphere. Winter means shorter days, so more night. X is in the southern hemisphere, and in the southern hemisphere you can see that the southern hemisphere is tilted toward the sun, and it is summer. Remember, in the summer we have longer days or shorter nights. So now that I've analyzed my diagram, I can answer the question. B says it is location at winter. It is winter at location X. I'm going to stop there. It's not winter at location X. X is tilted toward the sun. C says there's more hours of daylight at location X. Well, yes, it's summer there. Then Y. Which of these locations on Earth experiences the least change in the number of daylight hours throughout the year? Another way to phrase least change is about equal. So use your root words. Equal, equator. Near the equator, you have the least change in the number of daylight hours. For the most part, it's equal day and night. 12 hours day, 12 hours night when you're at the equator. The next section we reviewed is lunar phases or moon phases. And before we even do our moon phases, we're going to draw out a really simple moon phase diagram. And let's start with the sun, because the moon, remember, doesn't have its own light source. We only see the moon because it's reflecting the light from the sun. And we have the earth in the middle, and then the moon travels around the earth. We have the moon when it's between the earth and the sun, and then it's going to go counterclockwise, and we can talk about 8 different positions or phases of the moon. Remember, that's about a 4-week cycle. So moon and month, those have the same root. It is not a coincidence. They sound alike. When we think about the moon's phase or what it looks like, we need to remember perspective from Earth. So half the moon is illuminated, the half that's facing the sun, but when the moon is in between the Earth and the sun, we don't see the illuminated half. We see darkness. We see a new moon or nothing. Conversely, halfway through the cycle, about 2 weeks halfway through, we go from new all the way over here. If we look out, we're looking at the full illuminated portion of the moon. That is called our full moon cycle. When we go from new to full, the moon is waxing on the right, growing bright. When the moon is going from full to new, it is waning on the less and less. So describe what a waxing moon phase is, include what side it is seen. Getting bigger on the right. Waning on the left, less and less. So it is getting smaller on the left. So remember, everything about the moon is a pattern, but it's gradual. When we have a new moon, we don't see anything. It will gradually grow or wax on the right until it is all the way full. So waxing happens between new and full. Once it's full, it can't get any bigger. It's going to get smaller or wane, and it will gradually decrease. We see less and less light on the left. So waning is from full to new again. How many weeks are there between full moons? This entire thing is a 4-week cycle. How many weeks are there between a new moon and a first quarter moon? Well, if the whole thing takes 4 weeks, to go 1/4 of the way around takes 1 week. How many days between a waning gibbous and a new moon? So gibbous, remember, it kind of has the word big in there. It's backwards, but gibbous, it's big, it's almost full. So it's waning is right after a full moon. Here's my waning gibbous here. How many days between a waning gibbous and a new moon? If it takes 4 weeks to go all the way around, or 1 week to do a quarter, it takes 3.5 days between each. So from waning gibbous to third quarter, 3.5 days. From third quarter to waning crescent, we're up to 7. To new is approximately 10.5 days. A student keeps a record of the phases of the moon for 1 month. On the first night of the student's observations, the full moon is visible in the sky. After the full moon, which of these students will the student observe next? Once it's full, it's going to start to decrease in light, so it will begin waning. It's going to still be nearly full or big. It will be a waning gibbous moon. The diagram below shows 4 consecutive moon phases. Which of the following diagrams shows the next 4 moon phases in the correct order? So notice the light is on the right. We're waxing on the right, growing bright. So we have waxing crescent, first quarter, waxing gibbous, full. So if these are my waxing phases, afterwards I need to have waning phases. It's going to gradually wane or decrease, and I'll see less and left, and the white part will be on the left. So I'm not going to have another full moon. I'm not going to have full moon and then all of a sudden jump down and only see a little sliver. And C doesn't show enough of a transition. B, after a full moon, I have waning gibbous, third quarter, waning crescent, new. Two friends want to go for a night hike when it is a full moon in July. If there is a third quarter moon on July 2nd, so I'm going to label that third quarter, when is the approximate date of the next full moon? So I am a visual person. I'm going to go back to my drawing that I drew. If I am at new moon, 1/4 of the way is first quarter, full moon. Here's my third quarter moon. How long does it take to go from third quarter to a full moon? So third quarter, 1 week, 2 week, in 3 weeks. Here's my third quarter, 1, 2, in 3 weeks we will be at a full moon. So 1, 2, on the 23rd, it is a perfect time for a night hike and seeing a full moon. The diagram shows 4 phases of the moon as it revolves around Earth. A student builds a model based on this diagram. The student uses foam balls to represent the moon and Earth and a flashlight to represent the sun. The student should place the flashlight of the model where? So this is asking us to identify where the sun is. If my new moon is over here, where is the best place for the sun? The top, the left, the bottom, or the right? My sun should be over here. Remember, during a new moon, we are looking at the back of the moon, the side that's not getting light. During a new moon, the moon is situated in between the Earth and the sun. So the light source should be at position 4 in order to make this model correct. We reviewed components or parts of the universe today. Nebula is a huge cloud of dust and gas where stars form. It's the birthplace of all stars. Sometimes they're called a stellar nebula. These are also created after stars die. So when really big stars are at the end of their lifespan, they do a supernova, they explode, and their remnants, the pieces of those stars, get ejected into space to become part of this life cycle of stars, another nebula. We live in the Milky Way galaxy. Remember that galaxies do get classified by their shape. The shape of our galaxy, we are a spiral galaxy. Which of these correctly compares the masses of different objects in the universe? So a moon has less mass than a star, yes, and more mass than a planet. No, the moon is not larger than the Earth. A moon has less mass than a galaxy, yes, and more mass than the star. No, moon is not more massive than the sun. A galaxy has less mass than a moon? Nope. A star has less mass than a galaxy, yes, and more mass than a planet. We've also looked at how do we read an HR diagram. And remember that this is a graph of luminosity, which just means brightness, to temperature. And so stars that have a high luminosity are bright. So if the number is high on the Y value, it is a bright star. Or if it is low, it is not bright or dim. And remember temperature, if we look at the numbers, they're kind of weird. The numbers go backwards. So my larger temperatures means that my hot stars are over here, and then the numbers are decreasing. My cool stars are on the right-hand side. So if I wanted to check and compare these stars and list them from coolest to hottest, my coolest stars are going to be over here on the right, and then go that way. So as I go through my answer choices, let's see. Spica, I'm going to eliminate that one right away. Spica is the hottest star. It's all the way over here. B starts with Proxima Centauri, which is here. And then it goes to Betelgeuse. That's a little bit hotter. And it goes to the Sun, a little bit hotter. And then Spica. We can also compare stars using an HR diagram, looking at how do we compare one star to a second star. So star 1 is up here. So it's kind of hot and bright. It's in that upper corner. Star 2 is kind of just medium in all categories. So star 1 is cooler and less bright, No, remember our hot stars, and here my temperature value is on the top, but it's really the same thing. So again, I have hot and cool as far as temperature. Star 1 is not cooler. Star 1 is hotter than star 2, and it's brighter. It is higher up. We reviewed boundaries and how do we describe the plates that make up the surface or crust of the Earth. Divergent is to split apart. You can get seafloor spreading, so this happens in the ocean. And seafloor spreading, if you remember, results in mid-ocean ridges. So in the middle of the Atlantic Ocean, for instance, the two tectonic plates are splitting apart. The mid-ocean ridge or the mid-Atlantic ridge is growing, and in fact, part of it has grown up over the surface of the water to form the island of Iceland. When two continental plates diverge or split apart, the land kind of like drops between them and forms what's called a rift valley. There's a famous one in Africa called the Great Rift Valley. Convergent is to collide. When you have convergent plate boundaries, they generally result in mountain ranges. Sometimes you get subduction, which is a type of convergent boundary. Sub is below. So you have one plate going below another plate. They are converging. Anytime you have subduction, anytime you have one plate go under the other, you have a couple things happen. The first is you get this really deep area called a trench. So as your hands, like if you kind of look at my hands and one subducts or dives, that V, that deep area is my deep trench. But then that melted plate, that melts, and that melted plate comes back up. That melted magma, or when it gets above the surface, called lava, comes back up and we get a volcano. Transforms, kind of boring. They don't make any landforms. They slide past each other. Sometimes friction, it can build up, and then you get an unbalanced force that causes an earthquake. And if you remember, the thing that makes those tectonic plates move around is the stuff that's underneath the tectonic plates. We have convection currents in our mantle. And so that uneven heating, the mantle is heated by the hot core. That heated, less dense mantle rises toward the surface. It cools at the surface and sinks. And this cycle is continuous. So this is a conveyor belt, and the stuff on top of the mantle, the little pieces of earth or tectonic plates, move because of those convection currents. If we were to look at the map of the Earth's plate tectonic boundaries, this shows us different types of boundaries and asks, where would we most likely find volcanoes? Volcanoes happen at plate boundaries most of the time. So I'm not going to find volcanoes most likely at W, because that's not at a plate boundary. That's in the middle of a plate. Y is in the middle of the plate, and X is in the middle of a plate. Z is right on that tectonic plate boundary between the Nazca plate and the South American plate. These are the Andes Mountains in South America. These are definitely volcanic. Last, we looked at topographic and satellite views. Topographic maps are showing the contour or the 3D shape of land on a 3D map. Interval is how much does it go up by. Sometimes we just read a key, sometimes we have to figure it out. So if I look at my contour lines, my lines that connect points of equal elevation, they are going up by 10. So the interval would be 10. The steepest part is where the lines are closest together because the elevation is changing quickly. In number 72, we're asked to find a difference, so think math, we subtract in elevation between locations of the ranger and injured hiker. So we need to know the elevation of both the ranger and the hiker. The contour interval here is 50. So the hiker is up at point Z, and the line Z doesn't have a contour marked on it, but right beneath it, that line is 2,000. They go up by 50. So Z must have an elevation of 2,050 meters. My Ranger is marked on this line an elevation of 1600. So to find the difference, I subtract. And last, if a student stands at point marked X on the topographic map below, what height in meters must the student climb in order to reach the top of the hill? So as I look at my diagram, I need to remember to use my contour intervals and figure out what does the student start at. So the contour interval is 10, so that means that the lines go up by 10. This must be at sea level because here is 0. So 10, 20, 30, 40, 50. So they start at 50. We have to figure out where they end because we want to know what must they climb. This is similar to the previous problem. We're going to have to find the difference. So they start at 50 meters. They want to get up to 303. So if I subtract and find the difference, it would be 253. And when we do these on a computer griddable, instead of bubbling the answers, we just find the decimal and we make sure we use the correct place values, 253. You don't have to put zeros afterwards. It's not wrong to, but it's not required to. It would be right or wrong. Same thing here. We could choose to put a 0 there. It's not going to change the value, but it's not required either. Do let your teacher know if you have any questions and make sure that you guys are ready for your STAR test or your final exam packet.